idea that they have to use a formula. And the formulas, don't get me wrong, they're useful and you'll get the same answer, but sometimes, especially if you have a table with the original data, the formula just makes it harder. Because we did probabilities the first day, our basic probabilities, before we ever had all these formulas, because we were able to just look at the original data and say, okay, how many people in my class were girls with blonde hair? And I physically just count. I didn't have to say probability that they were girls, or times probability that they were blonde, given that they were a girl. We didn't have to do all of that. So if I'm looking at this, I want the driver to be a male and over age 59. So we can do a formula, or can I look at my table and find out how many males are over 59? Yeah, males over 59, that's those people. So if you add those up, you get 1,196. If I don't give you a given, it is out of everybody. What did everyone in this table add up to? Okay, so if we do that, we get 0.1119. B. The driver is female or under the age of 30. So you can do an or formula, or I could look at the table and say, okay, I need everybody that is either a female or under the age of 30. So I've got all these females, but then I also need those two males added in there. So I don't have to use the formula. I can just go through and add up everybody I'm interested in. So that gives me what? 6,728 or 10,691, which is 0.629. Right. When I give you a given, that's your denominator. So between the ages of 20 and 49. So the only thing I'm looking at is everybody from 20 to 49. So I am completely ignoring everything else in my table. That is my denominator. So the bottom of my fraction, if I just add up those 6 values, we get 5,294. Then the top is from those, how many were females? So if I add all those up, what'd you get? 2636, is that right? Okay. Divide those and we get 0.4979. Strongly encourage on this quiz tomorrow, show me this fraction. So if you had the wrong decimal, I can kind of see what numbers you had. Did you have the right numerator and the wrong denominator, or vice versa? Show me what you're dividing. The last one, my given is the driver is female. So all I'm looking at is my females. So my denominator will be the number of females, which is, and then the numerator is ages 20 to 49. So only out of the ones I'm looking at, the 20 to 49 would be those 3 values. I get 0.492. So if you have a given, that's when your denominator changes. If you do not, the denominator stays the same. Questions there? Number 2. So we have 3 traffic lights between your house and a friend's house. Each light may be red or green. List the sample space. When I ask you for a sample space, what am I asking for? All the possible answers. So we have 3 lights, so it could be red, 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 green, red, green, red, green, red, red. That's two reds, so if I only have one red, it could be red, green, 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 red, green, 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 red, or all green, 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 green. Alright, how many different combinations do I have there? 8. Okay, so the probability of stopping for exactly one light. So you stop when it's a red light. Stopping for exactly one tells me I have one red light. So how many of those combinations only have one red light? 3 of them out of my 8 total. So we get 0.375. What's the probability that you will have to stop for at least one red? That means you're going to stop at least once, so it's everything except all green. So that's 7 times, and you get 0.875. Is that one okay? Number 3. So, I'm telling you that A and B are independent. Independent means knowing one thing happens does not change the probability of the second. So, the probability of B given A, if these things are independent, has to be the same as the regular probability of B. So that is 0.1. The probability of A and not B. Look at your formula sheet. You have a multiplication rule for independent events. It's like top of the second page. And it says if they're independent and you want the and, all you have to do is just multiply those probabilities. So the probability of A we are given is 0.8. How do I find the probability of not B? 1 minus 0.1. That's 0.9, so 0.8 times 0.9 equals 0.72. Alright, C. Probability of not A or B. So if we use our formula, it's probability of not A plus probability of B minus probability of not A and B. So probability of not A would be what? .2 plus the probability of B is 0.1. These are independent, so to find the and, we already did one like it on the previous question, you just multiply it. So just 0.2 times 0.1. So we get 0.28. Is that okay? So problem 4. So we have a survey about vacation habits. So we've broke these people into what kind of area they lived in and how many days they vacationed. So the probability they spent 8 or more days. Okay, there's no conditional, so it's everybody. So 8 or more, that was 133 out of the 332 total, which is 0.4006. B, I want them to be urban and 8 or more days. So we could use an and formula, or we can just look at our table. Because I have the original data, urban, 8 or more days, that was only 21 people out of my total. So we get 0.0633. C, the probability that they were rural or spent 1 to 7 days. So it could be rural, it could be the 1 to 7. You don't have to use the formula, you can just add up how many people am I talking about. So these 90, if you just add the 164 and the 199, what's wrong with that? You double counted those 90 people. So you either need to just add these numbers, or you have to subtract off what you double count if you just added the totals. And so we should get, what, 273, is that right? Oh, my total. And that turns out to be 0.8223. Okay. Next one, I got into the givens. When you have a given, that's when we're talking fractions. The denominator is our given, which was suburban. So I am only looking at these suburban. So my total suburban is 95. Just out of those suburban, how many were 8 or more days? 38. So you get 0.4. E, I want them to be rural, given they spend 1 to 7 days. So my given is my denominator. So that's my 1 to 7 days. So there are 199 of those. Out of them, I only want the rural ones, which would be 90. So 90 out of 199 is 0.4523. So if it's a given, you're only looking at part of your denominator. Otherwise, it's the entire thing. Is that all right for everybody? Number 5. Okay. So we have different kinds of grapefruit here. Part A, we want the probability of being seedless. So if it's seedless, it could be pink seedless, it could be white seedless. Is there any overlap there? No, it can't be both. So you just have to add those probabilities. So 0.1 plus 0.2 is 0.3. Right, pink or seedless. So we need to add in the pinks and the seedless. So you can use a formula, or you could just say, okay, I need everything that's either pink or seedless. So pink seedless would work, white seedless would work, pink with seeds would work, but white with seeds would not. So you have 0.1 plus 0.2 plus 0.3, which is 0.6. Okay, then I got into my givens. The given is when you change your denominator. So given it is seedless. So I'm looking at my seedless. Probability of being seedless was 0.3. Out of those, only the seedless ones, how many were pink? 0.1. So you get 0.3 repeating. Alright, next one. Seedless, given it is pink. So my denominator is all pinks. So that's 0.1 and 0.3, so 0.4. Out of those, which ones are seedless? 0.1, and so we get 0.25. Any questions there? Number 6. I'm telling you they're independent. So we have a multiplication rule. We have 2 multiplication rules, 2 and formulas. There's one if they're independent, and then a regular one. Since they're independent, you can use the first formula at the top of the second page. The probability of A and B is just probability of A times probability of B. So plug in what we know. by the 0.8. So the probability of B is 0.5. Okay. I want to know on number 7 if these are independent. And I didn't give you a whole lot to go on. But if they're independent, if you're looking at the formula sheet, what we just used was the multiplication rule for independent events. So if they are independent, this has to work, that the probability of A and B is just the probability of A times the probability of B. So if I plug in, we get 0.08 equals 0.32 times 0.11. Are those equal? No. If they're independent, the formula has to work. It doesn't work, so they are not independent. They are dependent. Okay. Problem number 8. If probability of A is 0.4, probability of B is 0.5, and they are mutually exclusive. As soon as you see mutually exclusive, that tells me that the probability of A and B is what? 0. So you can use either or formula here. The first one is for disjoint events. That means mutually exclusive. But if you tried using the other one, when you subtract off the A and B, it's 0. So you're going to get the same thing. So 0.4 plus 0.5 is just 0.9. Is this helping at all? Is it beneficial to go over these? Problem number 9. Okay, what I suggest is make a list of what we have. The probability that he or she will want the job, event A, so the probability of A is 0.68. The probability that they want the candidate, and I said that's B, so the probability of B is 0.36. Probability of A given B is 0.88. So probability of A and B. They aren't independent, so we have to use our general multiplication rule. We've talked about different ways. Since we have A given B, the first thing we multiply by has to be the probability of B. So the probability of B is 0.36 times the probability of A given B, 0.88, and that gives me 0.3168. If I want B given A, we're using the same formula, but we're flipping it around. So it would have to be the probability of A times the probability of B given A. Is everybody comfortable with how I'm flipping those variables? So that and was given to you on the formula, and you can flip the A, B as needed. I know from part A, the probability of A and B is 0.3168. Probability of A is 0.68. So then we just divide, and we get 0.465. How will I decide if they are independent? If they're independent, what has to be true? Sorry to interrupt. Okay. They can't affect each other. So if they're going to be independent, then the probability of B given A would have to be the same as the probability of B. Are they? No. The probability of A would have to be the same as the probability of A given B, and they aren't. So no, they're not independent. What does it mean to be mutually exclusive? Can't both happen. Well, the probability of A and B, did we get 0? No, so these are not mutually exclusive because probability of A and B is not 0. Alright, does that make sense to everybody? Let's talk about problem 10. So this one was looking at flipping coins, but we don't have normal coins. The first one is a weighted coin and the second one is normal. So the probability of both heads, so heads and heads. What's the probability of getting a heads on the first one? 0.6. What about on the second one? So if you multiply those, you get 0.3. Okay, exactly one head. That means it could be heads on the first and tails on the second, or it could be tails on the first and heads on the second. What's the probability of getting a heads on the first one and tails on the second? Or means plus tails on the first. What's the probability of that? And heads on the second, 0.5. So you get 0.3 plus 0.2, so 0.5. Neither heads. If neither one is heads, that means you have tails and tails. So the first one, probability of tails is 40%. Second one is 50. So you get 0.2. Then we get into the conditional. When you have a conditional, your denominator changes. So in the first one, coin A shows a head. So the probability of a head on coin A is 0.6. The numerator, they both show heads. So that was part A. Probability they both show heads is 0.3. So we get 0.5. Okay, second one. The probability they both show heads, given coin B shows a head. So the probability of a heads on coin B is 0.5 because it's a weight or a normal coin. Alright, and probability that they both are heads is 0.3, so you get 0.6. Then F. Probability of a heads on coin A given exactly one head shows. So from part B, the probability of exactly one head was 0.5. The numerator, we have to think just a little bit more on this one. A heads on coin A. We already know that there's one head, right? And if there's only one and it's on coin A, then that means coin B is tails. So that means heads on A and tails on B, which is a 0.3% chance. So 0.3 over 0.5 is 0.6 again. Alright. So at problem 11. So we have tires, salvage from train wreck. We have 15 total, 5 have internal damage and 10 are good. You purchased 2. So the probability that both are damage free, so that means you have a good tire and a good tire. What's the probability that the first tire is good? If you've already taken one good tire, what's the probability the second one is good? We multiply and we get 0.4286. Okay, probability that exactly one is damage free. So that means we could have a good one and a bad one. Or we could have a bad one and a good one. So the probability that the first one is good would be, and if that one's good, probably the next one is bad would be, or, so plus, the first one being bad and the second one being good, Part C wants at least one of the tires to be damage free. So that means I could have one good tire or I could have two good tires out of this. In Part A you found probability of two good tires, in Part B you found probability of one good tire. So all you have to do is add those together. So we get 0.9048. Is that okay? Let's look at problem 12. So if I ask for a probability distribution, I'm asking you to list a table where you make x and the p of x. Hey guys, will you please keep track of how many of those pairs you're taking down so we make sure we get them tonight? Thank you. Okay. So we have to list our x values. So that's our 1, 2, 3, 4. And then how do we get our probability for each? Plug it in the formula. So 1 squared plus 5, so 6 out of 50, 0.12. Plug in a 2, you get 9 out of 50, so 0.18. Plug in a 3, 14 out of 50, so 0.28. Plug in a 4, 19 out of 50, so 21 out of 50, 0.42. If it's a probability function, that means every probability has to be between 0 and 1, and that's true. And they have to add to 1. Does that add up to 1? It does. So yes, it is a probability function. All right. So we have worked the entire second review. The first review, I worked all that in my first hour class and that video was posted. So what I want you to do is take the rest of class, go to that video and watch the questions that you